So first, I would like to thank to organizers for giving me this very nice opportunity. I also need to say happy birthday to Professor Sharko. So I will talk about the orbit braids. This work is the joint work with Hao Li and Feng Min Li. So here is the outline of my talk. The first, I would like to talk about the history of the braids groups, and then I will introduce how to define the orbit braid and get the orbit braid group. Next, I will talk about the main results. Finally, I will give us some example and show you how to calculate the orbit braid group. Here.
Yes.
Here, just the history of the braids. In 1925, the Adi the first defined the braid and braid group. Actually, the idea and some work about the braids and braid group can be seen in the other the works before 1925. Yeah, here you can see that from the works of the Hurwitz and the Frick and Klein. Also, you also see that even in the Gauss notebook. After the work of the Adi, the subject has continued to further develop by extending the ideas of the braid groups or combining with the various ideas and the theory from the other areas. Here, you can use the homotopy theory to give another description about the braid group. The Fox and Rees just used the configuration space to give another description about the braid group. Also, the Briscoe just generalized the braid group to the more generalized braid group to all the finite cost groups. Also some application in the lower dimensional topology. You can use braid to construct the link invariant. The later Arnold just calculates the cohomology of the braid group. Also another connection with the other theory and errors, such as the theory of the free groups and the chain-segment theory, even the Young-Fox equation in physics. Yeah. Here, just origin the viewpoints of the braids by Adi. Adi think the one braid is a collection of the connected strings in the three-dimensional space, this one. and one breeds. Here the picture, you can think something like this. But if you do some definition, maybe you can do the definition for the breed. That means the one breed is think of as the atomic class. Yeah. Adding calculates the breed group, which is generalized by some generators with the two relations. This relation, yeah, and this relation. Each generator just has only one crossing. Here is sigma I, and just there are only one crossing between the I string and the I plus 1's string. Yeah. So yeah, in 1962, Fedel and Novelis introduced the notion of the configuration space. Here, just the definition. A topological space, the configuration space is defined this way. Just the subspace of the
Sorry, I get the call to. Sorry, the Morse connection. Yes,
Okay. Yeah. Can I continue?
Yes, please. Yes, we will lose the connection. Lost the connection.
Yeah. So at the same time, the Fox and Novelis shows that this results gave another description about breed group. This one is just isomorphic to the fundamental group of the quotient space. Here, all these configuration space, just this configuration space, divide this symmetric group. Recently, the people often define the breed groups from the viewpoints of the configuration space, giving a connected topological domain for it. Here, the symmetric group can act freely on configuration. Then, this fundamental group is defined as the breed group. This fundamental group, this quotient space, this configuration space is defined as the pure breed group. About the general case here, because this group is free, we can get the favoration. So we can get this short exact sequence. Here, I would like to give an explanation in the general case. In the viewpoint of the adding, you can use the pairs in configuration space to construct the breed. the first give a pass. Here, the starting point just some deviant points. The end point is maybe here the coordinate maybe the change, and you can do the permutation on the coordinates. And then you can use this path to construct a braid as this way. Yeah. You can for each coordinates you can get string. Yeah, is defined as this way. Yeah. In this way. So here, for the braid, there is relation equivalence. Usually, it just used as topic. This relation is equivalent to this relation. This one just ontopy relation. So using this one, you can get this theorem in general case. So now you can use the fundamental group of the audience configuration space to define the braid group. Here, just I would like to generalization of the braid group by Briscoe. Yeah, in 1970, the Briscoe generalized the concept of the classical braid group from the symmetric group. Here, the symmetric group is still a cost group, a special cost group. Briscoe just generalized this special case to all the finite cost group. Now, we call this braid group just a generalized braid group or adding group. Here, just cost group with this relation. You know, each element has the order 2 in the cost group. With this condition, yeah. Here, just a definition of the generalized braid group. You move this condition, then just generalized braid group just defines that just condition. Here is a geometric realization of the generalized braid groups. The first, we consider the real vector space. Here, W means a finite subgroup of the generalized linear group. Here, this subgroup generalized by the reflections. Then we consider the set of the hyperplanes such that this group here, the finite subgroup, is generalized by the reflection in each hyperplane. We also need this assumption. So arbitrary reflection and arbitrary hyperplane, the image is still in this set. Then we consider the complexification of this real vector space, also hyperplanes. Then we can get arrangements in complex space. Here, just complements of the arrangements. It's very easy to see that this group acts freely on this space. So we have the Gaussian space. Here, the federation. So we can get this exact sorting exact sequence. But in classical case, here that's a symmetric group. But now here that's the finite group. The later, Briscoe and Delinear showed that theorem, the fundamental group of this constant space, is exactly isomorphic to the generalized braids group. The universal current space of the constant space is constructible, so this space is the equivalence space. Now, this space, for this space, fundamental group is called the pure braid group. Here, the Volodymyr general the way to define, to give the notion of the braid group. The first choose connected topological manifold, the median action of the finite group, and then you just consider all the points of the free orbit type. And that means you just move the other points of the non-free orbit grid. Then, you can, in this case, the group in this space is just the action of the group on this space is free. Here, suppose this space is connected, then we have the federation with the fiber of this group. Then we can get this short exact sequence. The Volodymyr gave us this definition. Here, the fundamental group, this one is called the braid group. The fundamental group of this one is called the pure braid group. In this case, classical braid group from the configuration space, just the spatial case. Also for the generalized braid group by Briscoe. Also the special case. Here, just our motivation and M. We hope to build on the theoretical framework of the orbit grid. In this case, we need the G manifolds. Maybe the action is not free. Here is our strategy, which is to mix the original idea of the adding and the theory of the transformation group together by making use of the construction of the orbits configuration space. In the following, I just give this definition. This definition was the first given by Sharko in his thesis. Here we need the G space with an effective G group. And then the configuration space is defined as follows. Here, in the classical case, all the coordinates are distinct, but here we need all orbits of the coordinates are distinct. This is the definition of the orbit configuration space. Now we just consider case here. The G is the finite group. The X is the connected topological map of the dimension is greater than 1 with an effective action. So here the orbit configuration space is connected. Now I would like to talk about how to define the orbit braid. Yeah. The first fix points as the base points. Here, for each point, the orbit is of the free type. Here you also can do the permutation on the coordinates on this point. But this group here for this space, there is a natural G action. Also, there are also the symmetric the action of the symmetric group, but these two actions are not commutative. Yeah. Here, just now we just use the path in this space to construct the braid. Take the path, and using this path, we can get the braids. But if we forget the action, G action, this braid is the ordinary braid in the sense of the adding. But if the otherwise, situation is different. Yeah. Here is an example. This one, just the space is a complex plan with the Z2 action defined by this way. Now we just consider this case, just the two strings case. Let's look at the two braids from these two close paths. Two braids. This if we forget the G action, these two braids are same up to asymptotic, because you can do the definition on this string, go to around this way. And finally, you can this braid can be changed into this one. But in our case here, the space has the Z2x. For each string, there are the orbits. If we look at the orbits, here the first string there are some crosses on the first string on the orbital of the second string. In this case, this braid is not the same as this braid. Yeah. So now we just define the orbit, the braids. We need to consider the group action. Here, just here. From this path, we can get the braid, but now we need to consider the orbit braid. For each string, we can get the orbit of string. Finally, we just get the orbit braid. About that case, we also need to consider the orbit base points. For here, the x is just point in this space. I'm sorry, here, just this one. Okay. Here, just the orbits of the base points. There are also the natural operation. You can use the two orbit braid, you can do this one. But this operation is not associative because if we this one like the theory of the homotopy case, this situation, yeah, we need some equivalence relation. Here, let's look at the ordinary case. Yeah, for the ordinary case, this relation is the same. This relation. In ordinary case, we can use topic relation to give the equivalent relation between the braid. But in the equivalent case, equivalent as topic is not substance enough to be used as the equivalence relation among the orbits braids. Here, the example. This case, as before, yeah. We just consider this two braids. These two braids, if we forget the G group, the two braids are the same. But if we consider the G action, we look at this one. But here, because these two axes on this space has the fixed points. This here, the first string. If we consider the orbit case, the first string with and it's the orbit string. Yeah, there are some intersection. But you also can untangle this intersection. In this case, finally you can change this one. But this braid and this braid are not homomorphic. That means we cannot use the equivalent as a topic to define the equivalence relation about the orbit the braid. But we need to consider this G action. Here, just we give the isotopic with respect to the G action. This is not the equivalent isotopic, but we also need to consider the G action. Here, the third condition is the key point. We need to consider the G action. Here, the two braids condition and the second condition is natural, but just the first condition is key point. In this case, we can show that this, but here not orbit braid, just ordinary braid. Just we just consider G action. This braid, the isotopic with respect to G action. Also, yeah, that means also corresponding pairs homotopy. Then we can define the equivalent relation among obvious orbit braids. The two orbit braids are equivalent if there are some G elements in this group, such that this condition. Also, we can get this result in terms of the homotopy. Now, let's this one to be the set consisting of the equivalence classes of all the orbit braids. But now we just at orbit basis points. In this case, yeah, we can define the operation. But this, we know this operation usually is not associated. But if we consider the equivalent relation, that's the class, this is just associative. Then we can get the group. This one, the forms are group under the operation, this operation, which calls the orbit braid. Here, for each class can determine a unique pair. This is a very key point. Yeah. Also about this orbit braid, there are some subgroup. If we just give this restriction for the and for each pass, we just consider this classes with this restriction. We get the subgroup called pure braid orbit braid group. If we consider this restriction, we get the braid group. If the endpoint is the same as the starting point of the path, we just get the pure braid group. We just consider the homotopy classes of all the paths, this path. The starting just this base point. The end starting point is just this base point. The end points belong to this set. This set is just the orbits of the this base point under the two accents. Yeah. We get this set. Usually here, this path is not closed. But we also can define the operation on this side by this way. Then we can show that this one forms a group under the operation, which give a homotopy description about the orbit braid. There is isomorphism. But this group, usually, in this group, each path maybe is not. So we call this group is the extended fundamental group. Also, we can give a homotopy description about this is the subgroup of the orbital braid group. In the special case, if the G is trivial, that case is just an ordinary case. Here, the orbital braid becomes the ordinary braid group. Also, the group is isomorphic to the extended fundamental group. Also, we have this thought exact sequence. From here, we see that this group is isomorphic, the fundamental group of the unordered configuration space of this one. But if this case of the G's non-trivial will be quite different. But here is the main results. There are the 5 sorts of exact sequence. This one, and this one, and this one. Also, here is the main point of proof. Yeah, using this map, we can get the semi-direct product about this group and the symmetric group. And then we can define this homomorphism. For each class, we know each class can determine the unique pair, and we can get this homomorphism. And show that this lemma, this homomorphism is surjective. Using that, we can show the main results. Finally, I will show you the examples about orbit braids. Just consider this space with the 2 canonical axons. The one is just the ZP axon. You just do the ZP rotation on the complex plane around the origin. This action is not free. Fixes only the origin. But if we move the origin, the action is just free. Another action is just action by the 2 reflection. About this one, this orbit braids. So orbit configuration space, we just calculate. Here, the final, yeah, I'm sorry. Sorry. Hello?
Yes, we hear you. It's okay.
Yeah, okay.
You have to.
Yeah, I'm sorry. Yeah, maybe I have no time, right?
Or maybe 2 minutes to finish.
Yeah.
Is it okay?
It's just 2 minutes. Yeah, okay. Yeah. It just gets this two relation as same as the ordinary case. That we also can give the generator by pass. Yeah. Here, just a free action case. Yeah. We also get this results. For this case, we also get these results. Here, just for each generator, how to give a description by pass. We just can choose the explicit pass. Yeah. So yeah, here we can compare with the generalized braid group. For the two cost group, we know that the two orbit configuration space, this two braids can be classified cases and classifying spaces of the two generalized pure braid group. So in the viewpoint of the braid zone, we have the corresponding two source exact sequence. In our viewpoint, we also get to sequence. But here, this group is just the BN, this cost group. So in this case, these two viewpoints are same. That means just this generalized braid group is isomorphic to the orbit braid group. But in this case, the two viewpoints are not stable. But we can see that this group is isomorphic to the subgroup of the orbit group. So yeah, I would like to stop here. Thank you.
Thank you very much.